Lab 3 on magnetic fields of a bar magnet. So the purpose of this lab is to explore the concept of magnetic fields by observing a bar magnet and how the magnetic field changes with distance and by whether or not it is on axis. So by measuring the magnetic fields created by a real bar magnet and then using GlowScript to obtain results from the data, the relationship between magnetic fields and distance can be obtained. So some key concepts this lab explores the Biot-Savart law, which is the magnetic field created by a dipole with a magnetic moment at an observation location r relative to the dipole, so the equation can be seen here. And then distance dependence, which is kr to the n. And so an assumption for this lab is that all variables are consistent except for r. So the procedure is to find the magnetometer chip in the phone, find the distance between the magnet and the sensor that produces a magnetic field with an x component with a magnitude of 20 microteslas, repeat that 2 more times, find a distance to the sensor that produces a magnetic field with an x component of 70 microteslas, and repeat that 2 more times, and then repeat that for 120, 170, and 220, and then find where the net magnetic field has a magnitude of 100 microteslas and d perpendicular, and then correct the y component for Earth's magnetic field. So the measurements, the key measurements, so using the following equations and then plotting like these values, so the key equations are kr to the n, and then take the ln of that to find n. So n is calculated to be negative 3.18 and it is expected to be negative 3. So as we can see, it's pretty accurate. And off axis, we use the corrected y component by subtracting magnitude of Earth's magnetic field, and d perpendicular is calculated to be 0.1679 meters. So here is the experimental model and the computational results. So as we can see, like here are the arrows, and then mu magnitude is 0.67, and then here are the magnetic fields on axis and perpendicular. The values are right here, and we can see d, the magnitude, we're at 45 degrees, which is 7.9 times 10 to the negative 6th, and then like the vector form. And so let's take a look at the code to see how that works. So first, our physical constant is mu over 4 pi, and here we initialize the magnet and we find mu hat, which is, and then we get the magnitude of the magnetic moment. And here we get the function for the magnetic field. So here we set k to our calculated value, and here we have a function for the dipole, and then we scale b, and this is to, and then we set distance to 0.2 meters, which is one of the values that we're supposed to calculate. And here we set the observation locations. So 2 of these are on axis and 4 are perpendicular. And here we draw the arrows to represent the magnetic field on axis. So that can be seen here, and these arrows will be orange. And then we create 4 arrows to represent the magnetic field perpendicular to the axis, and these arrows are cyan. So as we can see, it's like a pretty similar formula for each of the 4. And then we visualize the magnetic field 45 degrees off axis, so we have d perp right here times the square root of 2, and then we create the observation location 45 degrees from the axis, and we draw an arrow to represent that, which will be purple. So all of these, like, we'll be able to see how the code works and the values when we run it. So here are the values, and then here are the arrows that we saw before. And so here are like the calculated values. And so what if we hadn't oriented the experiment to compensate for magnetic north and instead laid out the meter at some intermediate angle, the readings from the magnetometer would have been skewed toward magnetic north. So that's why we corrected for it. And if we were to stick 2 identical magnets together and run the experiment again, we would expect the magnitude of the magnetic field to be twice its current value, but the direction, this is supposed to be magnetic, but the direction of the magnetic field would be the same. Thank you.